Hello class, this is a video tutorial on the normal distribution. In this video we'll be looking at the standard distribution, a particularly special probability density function. It's actually so special it's given its own notation. It's called the normal distribution. In this video we'll be looking at the standard normal distribution. It's given the notation phi of z is equal to e to the power of negative half z squared all over square root 2 pi. Another way you can write it, I prefer it this way myself. It's 1 on square root 2 pi times e to the power of negative half z squared. Just as a point of comparison, if this was regular function notation, it would be given as f of x e to the power of negative half x squared all over square root 2 pi. So the z is just x and the phi is just f. The main appearance and features that we're looking for is the following. First, it's always positive. So the graph is always above the x-axis, or in this case the z-axis. Its y-intercept is that peak there. It's approximately at the coordinates 0, 0.4. It has asymptotes on y equals 0, which means as z approaches negative infinity, the graph approaches 0, so it gets closer and closer, never touching. Likewise, as z approaches positive infinity, the graph approaches getting closer and closer, never touching 0. It has points of inflection at 1 and negative 1, and its y value at that point is approximately 0.24. The graph is symmetrical about the mean. The mean, mode, and median are the same, so that point there at x equals 0 is the mean, mode, and median. And lastly, the z-score indicates the distance from the mean. So 1 is a distance of 1 from the mean. 2 is a distance of 2 from the mean, and so on. We'll put more importance on this distance later on. Since phi of z is a probability density function, then if we were to integrate it from negative infinity to infinity, its total area will be 1. We're actually not going to be required to be prove that or actually integrate it at all. Mainly, if you can recall that for any probability density function defined from the lower limit a to its upper limit b, if we take its primitive of b minus its primitive of a, its total area is equal to 1. In the same manner, if we could integrate this, we would find that its primitive of infinity minus its primitive of negative infinity is equal to 1. What essentially we're trying to say is that even though this goes to negative infinity and this goes to positive infinity, the total area inside here, including those between the asymptote, all add up to 1. Now, normally we require the integral of a PDF, which is f of x, in order to find the respective CDF, primitive f of x, in order to calculate probabilities. We, however, do not have techniques at this level to integrate this difficult integral. So we cannot use the methods that we learned for PDF and CDF. Again, normally we would take the integral, substitute the two values we're looking for to get the probability, if we could do that here, we would. Instead, in order to calculate the probability of, let's say, any negative infinity to the value of z, we have to use a Z-score table. Z-score tables calculate the area or the probability of the normal distribution. So if we wanted the probability of x is less than z, what we're actually finding is the probability from negative infinity, so all those little areas underneath here, all the way up to whatever z value we're looking for. And to do that, we just use this table. Let's do 3 examples first. I'm going to cut this video into 2 parts just to keep to not keep it go for too long. Actually, where's my table? There it is. Let's do the first 3. So to calculate the probability from, so just to reiterate, what this is actually looking for is from negative infinity to the z value of 1.7 of phi of z dz. Graphically, what it's actually calculating, I actually advise you all to graph what you're calculating, because later on it gets a little bit more difficult. We're actually calculating all this area up until 1.7. And to do that, we simply go to our table and find 1.7. So this area that I've highlighted in orange is equal to 0.9554. That's straight from the table here. That's one example. I'm going to cut the video short here because I've got 8 more examples to do and I don't want to take up your time. You can pause the video and give these a go yourselves. So I'll see you in the next video with these examples. See you then.